He's going to tell us whether or not we can rule out self-interacting dark matter using Dwarf spheroidal galaxies.
So hi, I'm Oliver Elbert, and as was introduced, I'm here to ask and try to answer the question, can we kill self-interacting dark matter? So just really quickly, right now in astrophysics we have this wonderful lambda cold dark matter paradigm, does all of these things really, really well, makes great predictions, but we don't actually know what the dark matter particle is. So just to go into a little bit more detail, when people talk about cold dark matter, usually they talk about WIMPs, weakly interacting massive particles, and as is implied in the name, weakly interacting massive particles have very low or zero effective cross-section for dark matter scattering. But there's no real evidence that the self-interaction cross-section for dark matter scattering has to be zero. And in fact, there are many well-motivated particle physics models that have non-zero SIDM cross-sections. I've listed a couple here. And perhaps most importantly, these SIDM models leave all of the great successes of CDM completely intact. So to illustrate this, here we have a large volume simulated by Miguel Rocha, both in CDM and SIDM. And as you can see, there's no discernible difference between the two, either visually or statistically. In fact, even if we zoom in on the virial volume of a small 10 to the 10 solar mass halo in, again, CDM or SIDM, you can't tell the difference. And it's only when we look at the innermost regions of these halos that you can actually start to discern which is which. In CDM, you have your typical Navarro-Frank-White profile with a 1/r cusp in the center. And in SIDM, you have a roughly flat isothermal core. And this isothermal core is actually pretty advantageous for SIDM models. One thing that it gives us is if you take the core density and multiply it by the core radius, you get a characteristic surface density of about 100 solar masses per square parsec. And this is right in line with this characteristic surface density that's been measured in galaxies all the way from dwarf spheroidals up to Milky Way-sized spiral galaxies. So this SIDM is able to reproduce this characteristic surface density essentially for free. Another thing is SIDM solves too big to fail. If you have a 40 kilometer per second halo, you turn on self-interactions, suddenly you can populate this halo with local volume dwarf spheroidals, or local volume dwarfs. All of this is well and good, but SIDM is actually pretty annoying to deal with. It slows down our simulations, it adds additional parameters to our models, so we'd like to get rid of it if we can. So the question is, can we kill self-interacting dark matter? And for a lot of people, the answer to that question is, haven't we already done this? And there have been traditionally a couple of very strong constraints on SIDM. One is from merging clusters, specifically the Randall et al. 2008 analysis of the bullet cluster, which pegged the SIDM cross-section at about 0.7 centimeters squared per gram. There it is. So another really strong cross-section comes from halo shapes, in particular Jordi Meralda Escudet's 2002 paper, which restricted the SIDM cross-section to below 0.02 centimeters squared per gram. So that's good and dead, except we may have spoken a little too soon. Updated analysis has actually revised these constraints up to above 1 centimeter squared per gram, which is well within the astrophysically interesting regime. And just one thing I'd like to point out really quickly is that all of these constraints come from large velocity scales. 300 kilometers per second or more. Most SIDM models actually have some velocity dependence. Excuse me. Most SIDM models have some velocity dependence. So just because you have a constraint of 1 centimeter squared per gram at the cluster scale doesn't mean that you have to have 1 centimeter squared per gram or less cross-sections at the dwarf scale. Also, all of these constraints were derived using dark matter-only simulations and analyses. And as was brought up earlier, in these halos, you actually have baryons. And baryons can give you adiabatic contraction. So in order to model this kind of contraction, we ran a bunch of isolated non-cosmological halos at various different masses. And in these halos, we grew the gravitational potential of essentially the galaxy that would be expected to live in that halo. So for instance, here we have a Milky Way galaxy in which we grew a Milky Way disk. So here I have a visualization, or a set of visualizations, looking down looking on the edge of the disk in CDM and SIDM, both using no disks, and once we have turned on the disk, allowed it to grow and given the halo time to contract. And what you notice is that while you see the expected contraction in the CDM halo, you also see a similar contraction in the SIDM halo. And in fact, the SIDM halo is more compact along the disk axis than the CDM halo, which implies that SIDM is actually more susceptible to to the shape of your baryon distribution than CDM is. So suddenly, constraining SIDM with halo shapes just got a lot more complicated. We can also examine just the simple density profile of the dark matter in these halos. So again, for our Milky Way halo and a Milky Way disk, here we have the dark matter profile plotted, and the CDM and SIDM look roughly equivalent within our resolved regions. We can also play around with what baryon distribution we're using, so we can shorten the scale radius of the disk, make a much more dark matter, or a much more baryon-dominated system. And in this case, you actually get higher SIDM densities in the central regions of the halo than CDM densities, which is a little weird. Well, not weird, but unexpected. We can also go the other way and increase the scale radius of the disk, make a dark matter-dominated system. And in this case, you actually do get a core that forms in the inner regions of your halo with SIDM. And so you can actually tell the difference between the two. But unfortunately, I would say, these densities are still greater when you have the baryons turned on than when you don't. So here in black, you have the CDM only, no baryon density profile, and this dashed magenta line is SIDM only, no baryon potential. And both of them lie below what you get with SIDM with the baryonic potential turned on, even with a Milky Way with a much more diffuse disk than actually exists. So we moved on to more dark matter dominated systems. Here we have an LSB analog with an LSB analog gravitational potential grown in it. And you can see that actually here the CDM looks roughly the same. The SIDM looks roughly the same. So it turns out that in halos with fewer baryons, baryons have a smaller impact on your halo, which makes sense when you say it aloud. So from this, we figured that if we want to make constraints based off of dark matter-only simulations, which are easier to run, take less time, the best case to do that is in dwarf galaxies, which are the most dark matter-dominated systems we know of. So here are visualizations of one particular dark matter only simulation I ran of a 10 to the 10 solar mass halo, both in CDM and in SIDM with increasing cross-sections here. So you can see as the SIDM cross-section increases, the central density decreases, and the core radius increases until you get to a cross-section of 50 centimeters squared per gram, which is large. Great, thanks. So in the 50 centimeters squared per gram halo, in the inner region, you actually have core collapse happening. Basically, the density is increasing with time, and that's actually important, and we'll get back to that in a little bit. But first, to actually make constraints, what we can do is we can use these dark matter-only simulations that I ran, along with the large group of simulations Miguel Rocha ran, all at 1 centimeter squared per gram, and we can look at the central densities of these halos and plot them versus the Vmax of each halo. And from this, we can derive a scaling relation, which is what we have here in this cyan dashed line. And so we can use this to extrapolate what central density we would expect for halos or for galaxies down at this low mass end. And this is where the local field dwarfs live. So if we plot those on this same graph, and here we have actually the implied central, or the implied density at the half-light radius of each dwarf versus their half-light velocities, which gives us a lower limit on the central density of these dwarfs. We can see that if any of them lie above our implied scaling relation, then that SIDM cross-section is ruled out, or it's at least certainly in a good deal of tension with our observations of the local dwarfs. But at least in this case, for an SIDM cross-section of 1 centimeter squared per gram, everything looks okay. All of the dwarfs lie below it, so that's allowed. However, we also ran simulations with higher cross-sections. So here, I'm going to draw your eye to the 5 centimeter squared per gram and 10 centimeter squared per gram simulations we ran. So these have much lower, or at least lower central densities, which would push this line down to maybe here, which puts these cross-sections in tension with the local dwarfs. So what that means is we can probably rule out cross-sections on the order of 5 to 10 centimeters squared per gram at the dwarf scale. However, once again, I want to bring up that 50 centimeters squared per gram cross-section. And, sorry, one second. Just note that, again, due to core collapse, it actually has a higher central density, which is actually pretty close to the 1 centimeter squared per gram density. And what this implies is that actually, due to this core collapse phenomenon, once you push the cross-section high enough, you actually are back into a regime where those SIDM cross-sections are allowed at the dwarf scale. So mostly what we've been able to do is potentially rule out these intermediate cross-sections, but cross-sections either below that or above that are still questionable. So just in the interest of time, I'll throw up my summary slide and throw it to questions.
All right, question. Mauro, can you?
So you already hinted at it with your word weird. My naive expectation would be if I adiabatically grow a disk, I make the density go up in the center, and therefore the cross-section or the interaction rate will go up, and therefore the self-interaction would dominate and bring the core down. I don't understand. So can you give me an explanation for why my intuition is wrong?
Yes.
Why adiabatic contraction actually makes the density steeper?
So I can go back to that slide here. So yeah, for this compact disk, what happens is actually the extra baryons in the center of the halo actually basically kickstart core collapse in the center beyond what you would expect in a dark matter only simulation. So basically, because you're allowing SIDM, you're allowing dark matter scattering, you can have this inverted velocity dispersion profile.
But if that's due to a core collapse that is initiated, then why does the core collapse there go to these very high Cuspy densities, whereas if you go to the 50 centimeters squared per gram, your core collapse does not proceed to a very Cuspy profile?
So that's actually something that I'm not 100% sure about, and I want to look into more. Because in the dark matter only simulations, it seems like it proceeds very slowly. Right. And yeah, that's definitely something that deserves further investigation.
So Oliver might disagree. Well, Oliver's just more conservative than me, so I'm going to give an answer, but I think he's just more conservative than me, so this is why he didn't say this. But I mean, if you look at the velocity dispersion profile of the 50 centimeter square per gram run without the disk growing, its velocity dispersion profile isn't strongly inverted. That is, it isn't that much hotter in the middle than it is in the outer part, and it's all about the slope of that velocity. You know, how much hotter are you in the middle than you are in the outer part? So when you get that reverse heat flux, that's the thing that drives core collapse. When you grow a really dense disk, or you have a lot of baryons in the center, that gives you that crazy, and that gives you that velocity dispersion profile that's getting very hot in the middle, and that's what drives the core collapse. It's really the velocity dispersion profile, whether it's much hotter in the middle or not. And so it comes down to the shape of the velocity dispersion profile, and when you have baryonic contraction, stuff gets so hot in the middle, there's a lot of heat to drive out, and then there's no pressure support for that stuff anymore, and it just contracts.
That's correct, and in that case, the left self-interacting dark matter, if I look at the cross dispersion profile, we have a normal because it's covered by core collapse.
Well,
I still have an inverted cross.
no, it should. So my guess is it'll still be inverted. So I've looked at the.
Core collapse hasn't happened.
It's happening.
It's in progress.
Yeah, it's happening.
When you can start.
Well,
Until you get close to sigma squared, it's constant. That's what core collapse.
No. These things start off sigma square constant. That's what SIDM halos
Yeah.
look like, and you have to give it a little kick so it's hotter in the middle to kickstart it. That's what he meant by it kicks off core collapse.
Yeah.
Anyway.
All right, we'll have to leave the rest of the questions for discussion. And so our final speaker for this session is Mauro Javalisco, who is going to tell us, well, yeah, let's thank Oliver first. And it's Mauro that's